Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are talking about the paper called machine learning. And in this and the next module, we will be talking about an interesting concept of machine learning, or the interesting method of machine learning called neural networks. This is even more interesting because it is based on the concepts are based on the neural network activity of our brain. So, these are the people responsible for creating this particular module and bringing it to its current shape. And now let us look at the learning objectives of this module. The learning objectives of this module are to understand artificial neural network classification methods. Artificial neural networks is also called as ANN. So, we will try to explain the working of an ANN, or the artificial neural networks, and what are its types and what are its applications. Then we look at outlining the differences between the different types of neural networks, also between neural networks and a methodology we saw last previous modules called support vector machines. We will also discuss the advantage or the pros and cons of artificial neural network. And then the the keywords that we will be using in this module are neural networks, linear models, and feed forward network. In this module we will be talking about these aspects. Remember, I already told you that the next module will also be about neural networks. Now, before we go further, let us discuss or see what a real neuron will look like from a very superficial or surface viewpoint. So, the cell structure consists of 4 components: the cell body, which is called a soma. This is actually used for processing the inputs. Then we have the dendrites. These are the component that accepts the inputs. Then we have axon, which will turn the process input to output, and then we have synaptic terminals, which is electrochemical contacts between the neurons, that is, they bring about some interaction between the different signals. So, these are the 4 components of the cell structure: some cell body and dendrites, which accepts and processes the inputs to do with the input part, an axon which will process the input and turn it to output, and synaptic terminals responsible for the interaction. Now, based on this neuron, let us look at the neuron metaphor. Okay. So, neurons, the main purpose of neurons is to receive, analyze, and transmit further the information in the form, whatever information we receive, in the form of signals or electric pulses. So, it will receive, analyze, and transmit this information or signals. That is the job of a neuron. So, similarly, the neuron metaphor that we have drawn in the figure here consists of a number of inputs x1 to xn, and each of these inputs are weighted by weighting functions, weights along the edges. And then after we consider all those inputs, weighted inputs, we will apply some function to all this set of inputs at each node. Okay. So, that is the neuron metaphor. Now, let us go further. What are the goals of neural computation? Okay, neural computation. To understand how the brain actually works, maybe, and then it is big, complicated, and made of lot of stuff that dies when you poke it around, I mean actual work. To understand a new style of computation, this is very important. This new style of computation at the time when neural networks came into the picture was very, very innovative. So, an innovative style of computation, and it is inspired by neurons and their adaptive connections. So, in our brain we have connections that are adaptive to the circumstances, to whatever signals we get. So, we are trying to be inspired by that and try to bring in sort of a little bit of adaptive computation. And then it is different from sequential computation because parallelly inputs are processed. That is what happens in our brain, and it is good for typical cognitive processes like vision, and bad for actual just computation, multiplication of large numbers and so on. And to learn practical problems, learn algorithms is useful, even it does not depict actually how the brain works, it does not actually depict that, but using that is itself a good understanding of problems. Now, artificial neural networks are built of densely, now we are coming to actually what artificial neural network are. They are built of densely interconnected set of simple units. Each unit of an artificial neural network is simple. It takes several real valued inputs and produces single valued output. So, this is the basis of any artificial neural network. It is built of first densely interconnected set of simple units. The simple unit will take several real valued inputs and produce a single valued output. Okay. Now, ANN is characterized by its architecture, its training or learning algorithm, and its activation function. So, it is based on its architecture. We will discuss what this architecture is as we go along. its training or learning algorithm, what is the algorithm you are going to use to train it, and its activation function. Again we will discuss this further as we go along. One motivation is to capture the highly parallel computation on distributed processes. So, this was the time when distributed processing had just come into the forefront of computer science, and one motivation of why this neural network or artificial neural network gained importance is because it was able to capture that highly parallel computations. Most ANN software run on sequential machine, but they try to emulate distributed processes. Okay, at that point of time when it started off. Now, all problems cannot be solved by neural network learning. There are certain appropriate problems that can be solved by neural network learning. So, it is well suited for noisy complex sensor data such as from cameras and microphones. In today's world, lot of information is consists of sensor data, especially in big data analytics and so on. So, this probably is a one way why neural network should be considered as an appropriate mechanism, and maybe we could work further on that. Instances are represented as attribute value pairs. So, you have instances represented by its features or attributes and its values. The target function output, what you want as output, may be discrete valued, may be real valued, it could be a vector of several real and discrete valued attributes. So, the output can be a combination of just discrete, just real, or a combination. The training examples may contain errors. This is another interesting property of learning using neural networks. Long training this is a negative, long training times are acceptable. So, here you cannot do it on a real time, you have to do the training offhand, and that you must accept will take quite some time. Fast evaluation of the target function is required. You want to do an evaluation on the target function, do the training and keep on changing it and finding it out. No need for humans to understand the learning of the target function. So, it is not that it is understood, you do not have to understand, interpret it and put it, it is done without that. That can be an advantage or a disadvantage also. Now, let us look at some of the uses of neural network and the pros and the cons. It is good to use in continuous domain with little knowledge. Its ability to solve problems that are difficult to define. You do not know how to define, you just give the input, tell it the expected output, it will probably solve the problem for you. Can be used when a good functional model is not known. If you know a good functional model, there are other methods of machine learning that are suited for such problems. It provides human characteristics to problem solving that are difficult to simulate. Otherwise, you would never have simulated human characteristics. It is flexible and easy to maintain, and it has fast processing speed because of parallelism, not fast training, fast processing speed. The disadvantages are the same disadvantage you said there, you do not know a functional model. So, it is not interpretable. You give the input, you get the output, you get it correctly, but it is a black box. Learning is slow. So, the training model, when you do the training, that learning is slow. Good generalization, if you wanted to have a good generalization, you may have to provide lot of input or data points. So, the linear models we can talk about first. So, linear models for regression and classification have the form y x of w is equal to a function summation of j to m wj phi j of x, where x is a d-dimensional vector, it is a vector, phi j are fixed, phi j of x are fixed non-linear basis function. We will come into detail about this again as we go along. Please note here, x is a d-dimensional letter that has been converted using a function, non-linear basis function, and you have a weight associated with this. Okay. Now, for regression, f is identity function, linear regression, and for classification, f is a non-linear activation function, general, you have general and linear regression. So, it could be a non-linear activation function. If f is a sigmoid, it is called logistic regression. So, f of alpha is equal to 1 by 1 plus e to the power of minus alpha. We have seen these this type of sigmoid being used in a lot of places, and if that is used, then this regression is called as logistic regression. So, these are the linear models, both you use linear models for both regression and classification. Okay. The difference lies in the type of activation functions that you use. Now, how do you extend these linear models? So, linear models have useful analytical and computational properties, have limited applicability because of the curse of dimensionality. As the number of dimensions increase, linear models do not work very well. So, number of polynomial coefficients needed for finding the means of Gaussians is very high, for example. So, you extend the scope by adapting basis function phi of j to parameters. So, instead of using a phi of j as function, you use it to extend it to using parameters. It will become useful in large scale problems, and both SVMs, that is the support vector machines we saw in the last module, and the neural network address this limitation of curse of dimensionality problem. SVM addressed it another way, we can address it in some other way, that is in neural networks. So, before we go further, let us look at some of the comparisons between SVM and neural networks. SVM, varying number of basis functions m, centered on training data points, select subset of this during training. Neural network, number of basis function m is fixed, so you can fix it, but phi j have their own parameters. So, phi j is that conversion from the input to using a nonlinear function. Adapt all parameter values during training. So, that is the idea of a neural network problem. So, you have yk x of w equal to psi of, that is the wkj, the weighting part, plus into h, and then you have the weighting part with the parameters phi represented by wj. So, let us look at SVM versus neural network. In SVM, training involves nonlinear optimization. Since objective function is convex, optimization is straightforward, it has a single minimum. Number of basis function is much smaller than number of training points. Relevance vector machine results in sparser models, so produces probabilistic outputs at the expense of non-convex optimization. Neural network, on the other hand, is a fixed number of basis functions and parametric forms. Multi-layer perceptron have layers of logistic regression models, also involves non-complex optimization just like SVM. At the expense of training, you get more training, you get a compact and faster model. Now, let us go back to the origin of neural networks before we go further. So, to find information processing models of biological systems, the term covers wide range of model, exaggerated claims of biological plausibility. Actually, it is just a basis, that is all. And biological realism imposes unnecessary constraints, so a lot of biological realism we are taking away. Neural networks are efficient models for machine learning, particularly multi-layer perceptrons, which we will be seeing as we go along. Now, network parameters are obtained in a maximum likelihood framework, we will come to that again. It is a nonlinear optimization problem, and it requires evaluating derivatives of log likelihood with respect to network parameters, and this is done efficiently using error back propagation. Now, let us look at a neural network per se. It can be viewed as a generalization of linear models. Each ANN is composed of a collection of perceptron grouped in layers. So, typical structure has 3 layers: input, intermediate and output. The intermediate is normally called as a hidden layer. That is a term that they have used from when neural networks came into the picture. So, you have 3 layers: input, intermediate and output. Okay. The intermediate is called as hidden layer, as I already told you. So, instead of having one hidden layer, you can have several hidden layers also between the input and output layers. So, this is an input, an example of an input layer, a hidden layer and an output layer, one hidden layer here. So, we will go to the first type of neural network, which is called as feed forward neural network. Here it is simple neural network, information travels in only one direction from input through the hidden layer to the output. There is no feedback or cyclic or cycles, it is a directed acyclic graph. It is the simplest and the most used one, and it is basically used for pattern recognition. So, this is the first type of neural network we will be looking at, the simplest one called the feed forward neural network. Okay. So, this is the feed forward neural network, no backtracking, no going back, no feedback. Okay. Now, let us look at this in detail. So, this is the next type of neural network, which is called as recurrent neural network. The recurrent neural network, the signal travels in both directions. So, you have from input to output and output to input. It is complicated and a little bit dynamic, can use the internal memory to process arbitrary sequence of inputs and used to learn temporal patterns, where time becomes, that was used for patterns, this is used for temporal patterns. This is called as recurrent neural networks. You will see that from the output layer back to the hidden layer, there is some feedback going on. That is the major difference. That is why we say signal travels in both directions. Now, before we go further, there are different types of neuron. So, the first one is a linear neuron, where the function that you use is linear. Then you have a logistic neuron, where the function you use is logistic, and here you have again a perceptron where you use stepwise. So, potentially there are other types of neuron also require a convex loss function or gradient learning when you use those types. So, let us go to the first type of network which we defined. Remember, it has signals going only in one direction and it is the simplest, called feed forward network. A neural network can also be represented similar to linear models, but basis functions are generalized. So, you have y of x comma w equal to a function of the whole thing, where j is equal to 1 to m wj phi j of x, okay, we will come to that in detail. So, here this function f that you use to process the input, weighted input, is called as activation function. For regression it can be an identity function, for classification it can be a nonlinear function as a sigmoid function for example. The coefficients wj are adjusted during training and there can be several activation functions. So, that is the activation function. The other type of function that you have in this equation is the basis function, which converts which uses the input and converts it using a function. So, this is phi j of x, a nonlinear function, example it could be tan of h of a linear combination of d input. So, this is like transforming the input into another space. Its parameters are adjusted during training. So, you have two types of input, functions, activation function and basis function. Activation function can be different types of functions. The coefficients wj associated here is adjusted during training, and here you have another function called the basis function whose parameters are also adjusted during training. So, the first layer, that is the input layer, contains d input variables x1 to xd as you can see, and m linear combinations of the form, because the inputs can combine in different forms. So, you have aj is equal to I is equal to 1 to d wj xi wj d xi, where j can vary from 1 to m. So, you have d input variables which can combine in m different ways. The subscript 1 indicates the parameters are in the first layer of the input. The parameters wji are referred to as weights and wj0 as biases. So, you can have two things, biases and weights. So, every input variable is multiplied by its weight along and then added to a basis function, bias function, which is wj0. So, quantities aj are known as activations, this particular activation function. So, let me just repeat this. Suppose you have d input variables, they can combine in m different ways. So, this is the equation you have, which is the equation for activation. Activation is equal to j to d, because there are d input variables. Wji of 1, that 1 indicates a hidden layer, plus wj0 of 1, which indicates a bias for the first layer, the hidden, first layer of the network, and you have that j is equal to 1 to m, because you have m combination. So, this is the first layer of with the basis functions. Then you have each activation aj that we saw in the previous slide is transformed using a differentiable nonlinear activation function. For example, zj is equal to h of aj. So, zj corresponds to outputs of basis function phi of x. So, now in the previous case we did not consider that x was transformed, but here we have x being transformed using a phi function, or first layer of neural network, or hidden units. That is where you have the hidden units. It can be nonlinear functions h chosen to be sigmoid. Two examples of activation function are the sigmoid, logistic sigmoid, and the tan h, which are given here. Now, the activation function is determined by the nature of the data and the assumed distribution of the target variables. How will it be distributed? Based on that, you can choose the activation function. You can consider a variety of activation function. So, sigmoid or the S-shaped is fairly common, called as logistic sigmoid, used for binary classification, or hyperbolic tangent called tan of h. And then you can also use sigmoid is one and the other is radial basis function, where zj is equal to I of xi minus wji the whole square. So, this is another method that they use, which is called as radial basis function. So, then you can have softmax used for multi-class classification, and you can have identity also, yk equal to ak, useful for regression. So, this is the softmax exponential of ak divided by j exponential of aj. Now, it needs to be differentiable for gradient basis learning, and can use different activation functions in each unit. It need not be the same activation function. We have here assumed that the activation function is same. The second layer of the activation functions values Zj are again linearly combined to give an output unit activations, we assume. So, A of k is equal to I equal to 1 to m, again the m different combinations, wki of 2 xi plus wk0 of 2, where k is equal to 1 to k. So, k is the total number of outputs that you need, okay, and because here we are not the combination, total number of outputs you need. 2 refers to the second layer. Output unit activations are transformed by using appropriate activation function to give the network outputs y of k. So, the outputs you can see there is y of k. So, you started with x1 to xd, then you used m combination. So, the hidden layer had m outputs, m as the number of nodes, and then the output will be the k in this particular example. So, the overall network function will combine all the layers, first layer, all the stages. So, you have the yk of x comma w, that is the final output, is equal to A of the m combinations, and which uses h into the d combinations plus the basis function of the inside, you can see is the basis function of the first layer or the hidden layer, and then you can see the basis function of the second layer. So, this is what you have. Bias function, I am sorry, not basis function, where W is the set of weights and bias parameters. Note the presence of both sigma and h functions. There are two functions that are used. Thus, a neural network is simply a set of nonlinear functions from input variables x to the output variables y of k, and controlled by a vector W of adjustable parameters. So, you have two types of W, Wkj and Wji, this corresponding to from input to the hidden, from hidden to the output. So, that is what is done, and for both you have different nonlinear function, one is sigma here and the other is h. So, the forward propagation, the bias parameters can be absorbed into weight parameters by defining a new input variable called x naught. So, here you have yk, the same thing we are using, but what we are using is, we are instead of using a separate weight parameters, we can absorb it by defining a new input variable. So, process of evaluation is the feed forward propagation through network. It is a multi-layer perceptron is a misnomer, since only continuous sigmoid functions are used. So, the feed forward networks connect together a number of these units into feed forward network. It is again directed as cyclic graph. Figure shows a network with one layer of hidden unit, which we have already seen the last layer, and it is implemented using this. We are just repeating the same thing that we said in the previous slide. So, this is the feed forward network. We have looked at generalized linear models in the form this, already we have seen this, where a function and Wj of phi j of x transforms the input, and j is equal to 1 to m is the connection type of connections you have. For fixed nonlinear basis function, phi of j phi can be just that. We now extend this model by allowing adaptive basis function and learning their parameters. So, now we are going to change a little bit adaptive. So, in feed forward networks, multi-layer perceptrons, we let each basis function be another nonlinear function of linear combination of the inputs. So, that we are allowing. So, starting with input x1 to x0, you construct linear combinations. These Aj are known as activations and pass through an activation function h dot to get the output Zj equal to Haj. So, you have this. So, you have here the input links, okay. Then you have the input function, then you have the activation function, then you have the output and the output links. So, this inputs are weighted by those functions, weights, and then given to the input function, which will take it and give it to the activation function, which will then take it and put it to the output. So, this is the feed forward network, and the representation power of the feed forward network depends on the width and depth of the networks. So, Boolean functions is represented by a network with 2 layers of units, where the number of hidden units grows exponentially, because you are using only Boolean function. Continuous function bounded can be approximated with an arbitrarily small layer by network with 2 layers of units. Arbitrary function can be approximated to arbitrary accuracy by a network of 3 layers of units. So, this is the representation power of feed forward. If you use Boolean, you need large number of networks to get the model correctly. Now, let us take a case of 2-class classification. So, here you have neural networks, you have 2 inputs, 2 hidden units, and tan of h activation functions. The red line here is the decision boundary for the network. Dashed lines there, the blue, are the contours for the 2 hidden units, and the green line is the optimal decision boundary for distributions of the data. So, multiple decision choices for the vector W for same mapping function exist. So, it is not that you can have only one, you can have many. Okay. So, network training, given a specified network structure, how do we set its parameters or the weights? That is the major question you have. So, here as usual we define a criterion to measure how well a network performs, optimize against it. So, for regression training data are xk and t and t and tn belonging to the real values. So, you can use squared error. This we have used in many places. You find out what is the difference between the input, the expected output and the output that you have got, and that error we take, and depending on that we use a square error. Okay. So, for binary classification this is another discriminative model. The probability of t given the weights is equal to n is equal to 1 to n of xn of tn 1 minus tn. This is the squared error, and you will get this. With this you can calculate what would be your error. Okay. So, the parameter optimization, the geometrical view of the parametric optimization is given here, where E of w is the error and delta E is the delta error. So, you have non-conflicts local minima. So, E of w surface sitting over the weight space. So, WA is a local minimum and WB is the global minimum. So, you need to find the minimum at point WC. It is a local gradient is given by the vector delta E of w. So, points in direction of greatest rate of increase of E of w. So, with this is a geometrical view of how you find the W. So, negative gradient points to rate of greatest decrease. With that you will consider that and try to find out the derivative of the error to get the parameter optimization. So, neural network learning problem, goal is to learn the weights W from a label set of training samples. Learning procedure has two stages normally. Evaluate the derivatives of the error function delta EW with respect to the weights W1 to WT. Use derivatives to compute adjustments to the weight given like this. So, 2 plus 1 is equal to W top minus the derivative of that. Number of weights is equal to T equal to D plus 1 M plus M plus 1 K plus M into D plus K plus 1 plus K, where D is the number of inputs, M is the number of hidden units and K is the number of outputs. So, that we have already seen. So, that will be the number of weights you will have to find out. So, there are different methods by which this can be done. The typical strategy for optimization problem of this sort is a descent method, which we discussed with the geometric model given this way. These come in many flavors: gradient descent, we will not go into the detail of this, or stochastic gradient, it can be done in either way. So, and you can also use the Newton-Raphson second order, which we have done for the derivatives. All these can be used here. Stochastic gradient descent is particularly the effective one. For good optimization, you run gradient based algorithm multiple times using different starting points every time, so that you get a good optimization. Redundancy in training, that is because you will get that because of the redundancy in the training data, and also to escape the local minima which we saw in the previous slides. So, computing the gradients, the function y of xn of w is implemented by a network is complicated. So, it is not obvious how to compute error function derivative with respect to the weights. Numerical methods for calculating the error derivatives use finite difference like we did here. How much computation would this take with W weights in the network? So, that is the problem, because the number of weights you have to calculate is quite large. So, it will be of the order of W per derivative or the order of W squared total per gradient descent. Use of gradient improves computation speed. So, what have we discussed in this particular module? We discussed the neural network basics and the learning paradigm, and then we discussed the pros and cons of neural networks and the types of problems that you typically handle using neural networks, and we explained the architecture and learning of a very simple learning network, which was called the feed forward neural network, which we had the signals going only in one direction. The major issue there was to find the W's such that the error is the least, and the weights were found by calculating the error between the expected output and the output that we get using the neural network, and then you keep changing the values such that the error is minimized using a derivative of the error. Method used to do this was the gradient descent. With that, we will stop with this module. In the next module, we will continue with certain other aspects of neural networks. Thank you.